I can also represent the probability distribution for a discrete random variable with finitely many possible values using a graph. And we've actually done this in the previous section for our probability distribution for experiment A and experiment AP, which actually had infinitely many possible values for the variable, but nevertheless it was discrete. So recall how I do this. I form a category which contains each value, well, a category for each value of the random variable, and I'm going to center it at that possible value of the random variable. And that category, or that interval, should not contain any other possible values of the random variable. And we make each category of equal width so that our final graphical representation adheres to the area principle. And above each category, we draw a bar whose height is equal to the probability of the corresponding value. If the possible values of the random variables are integers, then it's easiest just to make each bar have a width of 1, or a base with width 1. And here's our example. If I flip a coin 4 times, let x denote the number of heads, then we have the possible values of x are 0, 1, 2, 3, and 4. And here we've drawn a bar centered at each of those possible values. And the width of the base of the bar is 1 in each case, so they don't overlap. And the height of each bar is the probability that each of those possible values of x occurs. How do we use this graphical representation? Well, the graphical representation contains all of the information we need about the probability distribution. So we can actually use it to calculate probabilities. The total area of the graph we draw, the bar graph we draw, should be 1 if the base of each of the rectangles equals 1. And we can calculate the probability of any particular set of outcomes by summing the area of the graph above those outcomes. So here, for example, we have the probability distribution for a random variable x, a discrete random variable, whose possible values are 1, 2, 3, 4, 5, and 6. And the area of each of those bars is equal to the probability that that value will occur. What is the probability that x is less than or equal to 5? Well, it's actually the sum of the areas of the rectangles above 1, 2, 3, 4, and 5, which are now the blue rectangles. And we can see that that's 0.1 plus 0.2 plus 0.2 plus 0.1 plus 0.2. It's 0.8. Another clever way to do this is to say, well, the total area of the distribution is 1, and so I can calculate the probability x is less than or equal to 5 as 1 minus the area of the red bar, which is 0.2. So that probability is 1 minus 0.2, which is 0.8.